So those equations are true no matter what coordinate system we use. We could choose polar coordinates, rectangular components, we could choose cylindrical components, any kind of component system you could think of. That works because we've just represented those in terms of vectors. And the vectors can be represented however we want. Typically, a lot of applications, it's quite convenient to use rectangular components. We exist in three-dimensional space, and most things are quite convenient to model or write mathematically in terms of rectangular or Cartesian components. So how we do this is typically we'll write a vector and its x, y, z components, which are rectangular components, and they're always relative to a fixed reference frame. So here we have x, y, z as our fixed reference frame. And we have our position vector. We wrote that as r, and in this case, we can say r is equal to distance in x times our x direction unit vector. So we'll call that I hat, which is a unit vector in the x direction, plus our y component, plus our direction in the y direction, plus our z component, times our unit vector in the z direction. So I, j, k, j, k, these are unit vectors. In the x, y, and z directions. And then x, which is a function of time, y, which can be a function of time, z, which can also be a function of time, are just the components of the magnitude in those directions. So these are our x, y, z components. So we described before the magnitude. Think of magnitude as distance, the total distance away from an origin. So the length of a vector is the magnitude. So we can write the magnitude as the magnitude of r is equal to the sum of the squares of the components, all square rooted. So square root of x squared plus y squared plus z squared. This should be familiar, it's just the Pythagorean theorem. And then lastly, because it's a vector, it has a magnitude and a direction, we can write the direction as a unit vector direction that is along that position vector line. So we can say the direction, we'll define that as UR, which is our unit vector in the direction of our position vector. And that is equal to our vector R divided by the magnitude of R. So that's position. You can essentially do the exact same analysis again with velocity. So let's start with our definition of velocity. We said that velocity was equal to time derivative dr dt. We've written our position vector as components x, y, and z. So let's substitute that in. We get the time derivative d dt of our position vector. So our position vector was x I hat plus y j hat plus z k hat. So since we have taken a fixed reference frame, the components are constant. They're constant in magnitude, they're unit vectors, they're always going to have a magnitude of 1. And they're constant in direction because our reference frame isn't moving. Just the particle is moving with respect to our fixed x, y, z. So if I, j, and k aren't moving with respect to time, then they can come outside of our derivative, and then we were left with a simplified version, and we can say our velocity vector is equal to dx dt times I plus dy dt times j dt times k. So this would be our definition of our velocity with Cartesian coordinates. Now what we call each of these values here, dx dt, this is our x component of velocity, which we can also just call x dot. If we ever see a variable with a dot above it, that's referring to the time derivative. If you see 2 dots above it, it's the second time derivative. So Vx is our x component of velocity. Same thing with our dy dt. This is equal to our Vy, which is equal to y dot. And then dz dt is equal to Vz, which is equal to z dot. So those are the x, y, and z components of our velocity vector v. Same thing as with position. Our position vector has a magnitude and direction, so we can also write the magnitude of velocity is equal to the square root of the sum of the components squared. Vx squared, Vy squared, plus Vz squared. And we can write the direction is equal to the direction is equal to the velocity vector divided by that magnitude. And it is always tangent to the path. So that's velocity. Pretty straightforward. It's just the time derivative of our position vector. We have rectangular components, Vx, Vy, Vz, which are our x, y, z components of velocity. And we have a definition for our magnitude and our direction. Label this here. All right. Lastly, acceleration. And this is where sometimes it could get a bit confusing. But acceleration, if we just follow the same steps, can break down and it doesn't become too difficult. So we said acceleration is equal to that time derivative dv dt, which is equal to d squared r squared. And if we go by the same process as before, we can rewrite this as the acceleration components ax I ay j plus az k. So ax, ay, and az are all the components of acceleration acting in the x, y, z direction. And we can write ax is equal to of our velocity in the x direction, which is equal to the double time derivative of our x position, which we can also see vx dt. So if we know our component velocity in the x direction, we take the time derivative of that, we get our component velocity in the x direction. And we can write the same thing for all the other directions. Ay is equal to Vy dot is equal to y double dot. equal to the derivative of dvy dt, and az is equal to vz dot, or our z component of our position, z double dot dvz dt. So notice when we write these in component form, I'm not drawing vector arrows above these because these are no longer vectors. These are scalar quantities, and they're just the components of the vector quantity in each direction. So they're the coefficients that would go in front of our i's, j's, and k's. They're just scalar values. So again, we same thing with magnitude. Total magnitude of our acceleration, x squared, say y squared plus az squared, all to the power of 1/2. And we can write the direction is equal to the vector a divided by its magnitude. So we've talked about position, velocity, acceleration. Now let's write an example. So in a box sliding down a ramp, we have an equation for the path. Y is equal to 0.05x squared, and that's in meters. It gives us a velocity component minus 3 meters per second, and ax is equal to minus 1.5 meters per second squared at x is equal to 5 meters. And then it's asking find the y components of the velocity and acceleration of the box at that same point when x is equal to 5 meters. So let's begin just by writing down some equations that we know. We're asked to find velocity and acceleration, the y components. So what is the y component of velocity and acceleration? So y component of our velocity, vy, and this is equal to dx dt, or we can just write it as dy dt, which is y. So we have an equation for y. Let's use that. Let's take the time derivative of our function y is equal to 0.05x squared. So dy dt is equal to the derivative with respect to time, 0.05 x squared. How do we take the derivative of a function that's not really a function of time?
Would you just take the derivative of the first term and then multiply it by the x dot?
Yes, exactly. Very good. So x is a function of time, so we're going to kind of take the derivative of this with respect to time implicitly. So the derivative, we're going to pretend for now x is just a function of time, so we would get 2 times 0.05 x. And then to complete this, we have to write this using the chain rule times dx dt, which is equal to x dot. If we do this, we have an equation for our y component of velocity is 2 times 0.05x times x dot. So we have, basically, we're going to solve when x is equal to 5, and we're given our x component of velocity, vx, which is x dot. So we can rewrite this as 2 times 0.05 times 5 times our x dot, which is minus 3. So if we do this, we should get negative 1.5 meters per second. So that's our y component of velocity. Now let's do the exact same thing with acceleration. So our y component of acceleration, ay is equal to derivative of dvy dt. So we have an equation for our Vy, which is right here. So we can write time derivative of 2 times 0.05. Let's just write that as 0.1 x times x dot. So we take the time derivative of this. We use the product rule because we have two x's in here now, an x and an x dot. Take the derivative of one term plus that function with the derivative of the other term. So we end up with 0.1. Let's take the derivative of the first x, which is just 1. Get x dot, and then the derivative, the second term, we end up with 0.1 x times x. So we know x dot is minus 3, and we're given ax, which is x double dot, which is minus 1.5. We can substitute in 0.1 times minus 3 times minus 3 plus 0.1 times x now is 5, and the x double dot is minus 1.5. And we end up with ay is 0.15 meters per second squared. So this question, when you first read it, might not seem too obvious which direction to go. But if we just write down some equations we know that have the terms that are given in here, and just follow the steps, we can find some substitutions, and then it actually ends up not being as difficult as it first appears. Let's look at example 2. A particle travels along the path y is equal to 0.5x squared. When time is equal to 0, this particle's path is going through the origin. Find the particle's distance and magnitude of its acceleration when time is equal to 1 second if the velocity, the x component of velocity is equal to 5t feet per second, where t is in seconds. To solve this problem, it might be easier to separate this into the x and y components. So let's start with the x component. So we know the velocity, vx, is equal to 5t. So at t is equal to 1 second, we can write the position, or at least the x component of position, using our kinematic equations. We can say that the integral, the x component of velocity times dt is equal to the integral from 0 to t, 5t dt. If we solve this, the integral of 5t dt would be 5t squared over 2, or 2.5t squared over 2, 2.5t squared. So then at 1 second, we can write x is equal to, at 1 second, our x position is 2.5 feet. Then the other part it's looking for is its acceleration, so we need to find the x component of acceleration. So let's write that. The x component of our acceleration is equal to x, which equals to vx dot, so it's the time derivative of 5t, which is just equal to 5. So our x component of our acceleration is equal to 5 feet per second squared. And that's constant with respect to time, so at t equals 1, it's still 5 feet per second squared. 2. So now we've done our x components, let's look at our y components. So we know our position as a function of x, so we can write for our position y is equal to 0.5 x squared. So when t is equal to 1 second, we know that x is 2.5 feet. We substitute x is equal to 2.5 feet. 2.5 squared. And that would give us 3.125 feet. That's our y position. Our velocity is our vy. How can we find our velocity? We use the same process as before. We can take the time derivative of our function of y, which should be equal to 0.5 times 2 times x dot. And at t is equal to 1 second, we know our x component of velocity. That's up here. That's our x dot. We can say at 1 second, x dot is equal to 5. So this is just equal to 0.5 times 2 times our x position is 5, and our x dot is 5. So I get our y component of velocity is 12.5 feet per second. And then lastly, our acceleration, ay is equal to vy dot, or y double dot. So we can write this as 1/2 times 2 is just 1, so we end up with x dot times x dot plus x times x. We know x dot at t equals 1 second is equal to, where is that, 2.5. So we have 2.5 times 2.5. Our position is, oh, I confused position. Our x dot is 5, not 2.5. 5 times 5 plus 2.5 times our x component of acceleration. X component of our acceleration, ax, is 5 feet per second squared, so that's also 5. And then if we do this, we should get 37.5 feet per second squared. So we're asked to find the position, or sorry, the magnitude, find the particle's distance and the magnitude of its acceleration. So when we hear the word distance, we should think magnitude of position vector. So this is an x and y space, so there's no z term. So we can write distance is equal to the magnitude of our position vector, which is equal to the square root of x squared plus y squared. We know our x position is 2.5 squared, and our y position is 3.125 squared. So we get our total distance, which is the magnitude of our position vector, is 4 feet. And if we want to find the magnitude of our acceleration, lastly, the magnitude of acceleration is the square root of the sum of the components of acceleration squared. So we get the square root of ax, which is 5, I think. Yeah, 5. Plus our ay squared, which is 37.5, which would give us 37.8 feet per second squared. So again, we just followed the same step, calculated our components based on our path function, and found the components of our position and acceleration, and then calculated the magnitudes of those based on the components.